So we are also going to work with a lot of steady flow or steady state, things like that. You'll see steady. And so the term steady implies that there's no change with time. Okay, it remains the same. So if something is steady, that means that there will be no observable change over time. It's just going to be the same. And then, of course, the opposite of steady is an unsteady or transient. Okay, so just a little note, a large number of engineering devices operate for long periods of time under the same conditions, and they are classified as steady flow devices, right? And so you notice that long periods of time, because of course we know that if something is truly no change with time, then given an infinite amount of time, it would remain the exact same. Of course, we know that that's not entirely possible. So just like an isolated, nothing interacts, nothing impacts with its surroundings on the system. Just like we know an isolated system is not feasible and it's kind of an assumption, we say the same thing for steady, right? So for a long period of time. Steady flow process is a process during which a fluid flows through a control volume steadily, okay? Steady flow conditions can be closely approximated by devices that are intended for continuous operation, such as turbines, pumps, boilers, condensers, heat exchangers, power plants, refrigeration system, things that we need, right? You need your refrigerator to always work. You need the same amount of fluid to flow through it. You need the same output. You need those things to be very steady. You need them to be dependable. You need them to work around the clock. You don't ever need them to turn off, right, or need to be reset. So figure 132 shows during a steady state process, fluid properties within the control volume may change with position, but not with time. Okay, so you see in here, you see some microscopic changes. You've got mass in, mass in. You've still got the same temperatures over there. You've got 300, 250, 225, 200, 150, and you've got mass out, and you've got a control volume, right? So you've got all these changes. You see that it's coming in at 300 degrees Celsius. It's moving all around in our system, and the mass is exiting at 150 degrees Celsius. And the only change here is 2 hours. The same thing's happening, but 2 hours change. That's just like our refrigerator, right? I need it to work the exact same at 9 a.m. as at 12 p.m., right? And I need it to work the same as today as it's going to work in a year, right? I need it to work. So here we've got, again, just under a steady flow condition, the mass and energy contents of a control group remain constant. So this is just another one, and you see the denotation there. You've got the control volume of mass is constant. The control volume of energy is constant, okay? So when we're talking about temperature and the 0th law of thermodynamics, we're not going to get really into the 0th law, but just for you to know, if two bodies are in thermal equilibrium with a third body, they are also in thermal equilibrium with each other. How does that make sense? Well, let's talk about it. By replacing the third body with a thermometer, the 0th law can be restated, right? Because the first one, you're like, that doesn't, what just happened, right? Okay, so let's restate it. The 0th law can be restated as two bodies are in thermal equilibrium if both have the same temperature reading, even if they are not in contact. And so then you see here, two bodies reaching thermal equilibrium after being brought into contact with an isolated enclosure. So we see that isolated here. It had not been introduced before then, besides me just talking about it. So you can reach thermal equilibrium even in an isolated system, but with a firm boundary, not touching. Okay? We're not going to go too much into the 0th law, though. Okay, and so then here, what is really good is you start getting into temperature scales, right? So you've got all temperature scales are based on easily reproducible states, right? So knowing that they're dependable, such as freezing, boiling points, the ice point, or the steam point. So you've got ice point is, of course, 0 degrees Celsius or 32 degrees Fahrenheit. And again, you have that at 1 atmospheric pressure, right? Okay. And then you've got steam point, which is 100 degrees Celsius or 212 degrees Fahrenheit. You'll know that if you put a pot of boiling water on the stove, you can get it to the steam point because it will start to steam. Celsius scale, we talk about that as the SI unit, and then Fahrenheit scale is an EE unit. Thermodynamic temperature scale, it's just independent of the properties of any substance. You've got what we're going to use is Kelvin, which is SI, and then Rankine, which is E. And then a temperature scale nearly identical to the Kelvin scale is the ideal gas temperature scale. And the temperatures on the scale are measured using constant volume gas thermometer. We're going to start working with ideal gas, and you're going to start calculating things like that. So that'll make, just kind of put that on the back burner. But this is just talking about, you can see what the zero law did. The zeroth law, the main contribution is we've got temperature scales. That's basically what it's saying. You can freeze water at 32 degrees, even if nothing's contacting with it, all over the world. Okay, does that make sense? That third body, you can measure with it. Conversions right here, we're going to need these. So you've got Kelvin is equal, temperature Kelvin, so if you have 1 Kelvin, is equal to temperature Celsius plus 273.15. So that's your additional that you would add into that. So if you had 1 Kelvin, your Celsius would be 274.15, right? So you've got Rankine converting into Fahrenheit. That's a plus 459.67.67. You've got Rankine to Kelvin, which is a multiplier. And you've got Fahrenheit to Celsius. And that's like a y equals mx plus b situation there. And so then the reference temperature in the original Kelvin scale was the ice point, which is 273.15 Kelvin. Makes sense, right? Which is a temperature at which water freezes or melts, right? So just depending on which arrow of time you're using, if it's getting hotter or if it's getting colder, would be whether it starts freezing or starts melting. The reference point was changed to a much more precisely reproducible point, the triple point of water, the state at which all 3 phases of water coexist in equilibrium, which is assigned the value of 273.16. And so we've got all 3 phases of water. What are those phases? We've got liquid, we've got solid, and we've got gas, right? So we've got steam. And then here's some comparison of those temperature scales. Okay, and then every time you see this triangle, of course, just remember that that is change of. So the change in temperature Kelvin is equal to the change in temperature degrees Celsius. The change in temperature Rankine is equal to the change in temperature Fahrenheit. Okay, and then you've got some magnitudes of various units. But again, you're going to use the conversions. That's going to get what you need. And then we have, not going to really go into this. This is just a lot. Okay, now we're going to get into pressure. So a normal force exerted by a fluid per unit area, that is pressure. A normal force exerted by a fluid per unit area. So 1 PA pascals is equal to 1 Newton over meter squared. You've got the conversion to bar and what those are equal to. So bar is equal to 10 to the 5th pascals. It's also equal to 0.1 megapascals, also equal to 100 kpascals. So kilopascals. So you've got all of these. You've got 1 atmospheric pressure. You've got 1 kilogram per kilogram force per centimeter squared. You've got that going into newtons. And all of those equalities here and how to convert to get whatever unit you need. But again, I do have a sheet to give you guys, but this would be very helpful to copy down because you're going to be using a lot of this. Okay, so you see when we're talking about the pressure, A normal stress or pressure on the feet of a chubby person is much greater than the feet of a slim person. Probably not the best example here, but very accurate. So if you're 150 pounds, you're going to have less of a pressure, less stress on the feet than if you were heavier, of course, because it's just load bearing, right? So if you have a bigger bridge on, the supports, you're going to have more load, or you're going to have more. It's going to be under more stress than if you had a smaller bridge. Okay, and so you do see here that the area is the same. The feet area equals 50 square inches. So that is really important, right? Because those need to be the same for you to calculate and for it to withstand the stress the same. But here you do have a formula for pressure, and what you end up with is 3 psi. But you see, it's really not a difficult calculation to be had. So you've got area, of course it's given, things like that. You've got weight, so things like that. And so then you could do the same thing, but change this to 300, and then of course you'd get 6, right? Okay. Then when we're talking about different kinds of pressure, you've got absolute pressure, you've got gauge pressure, and you've got vacuum pressure. And so over here on the right, I do want to point out that the gauge pressure, P gauge, is equal to the absolute pressure minus the atmospheric pressure. Because we want to reduce, or we want to exclude the atmospheric pressure, right? Or the vacuum pressure is equal to the atmospheric pressure less the absolute pressure. So what do we get into? What does absolute pressure mean? It means the actual pressure at a given position, okay? It is measured relative to absolute vacuum, that is absolute zero pressure. Gauge pressure is the difference between the absolute pressure and the local atmospheric pressure. Most pressure measuring devices are calibrated to read zero at atmosphere. That's why you want to reduce this here. See, remember? So that they can indicate gauge pressure, because they know that when you're at gauge pressure, you want to exclude the atmospheric pressure. And then vacuum pressures are the pressures below atmospheric pressure, right? So you need to know what the difference from atmospheric pressure to absolute pressure is, right? We want to know that difference because we want to know what that vacuum pressure is. And in this text, P will denote absolute pressure unless specified otherwise, and that's because we always use that, right? So the figure 141 is, in my opinion, much easier to understand. So let's look right here. You've got atmospheric pressure, P ATM, okay? And you have it right here. You've got a red line that's denoting all the way across. It's your atmospheric pressure staying the same. Okay, so if you have an absolute pressure going about, that looks like 65, 70% of the way up, then what you have the rest of that way is a vacuum pressure. Okay, so look, if your P vacuum is equal to your atmospheric pressure less your absolute pressure, right? So you can get that vacuum pressure. And then look over here for your gauge. Okay, so you've got your atmospheric pressure still here. You've got your absolute pressure, which is way higher, and the difference between those two is your gauge pressure. So you can, the formulas work just fine, and you can write down the definitions, and those are important. It's important to know what it is and those assumptions. But in my opinion, the schematics and drawing these are the most helpful because it helps you visualize how they work together. So you do have variation of pressures with depth, of course, and so you've got the change of pressure is equal to P2 minus P1, so those state changes, right? And then you start getting into P is equal to pressure, the atmospheric pressure, plus GH, rho GH. So you're going to just start getting into all of these variations of pressures with depth, okay? But this is going to make a lot more sense when we start actually working into it. So I'm not going to go into it so far into this, which is just really covering theoretical. I'm not going to walk through every formula in here because I would rather us actually work them. So these are just free body diagrams, and you can see, gauge pressure here and when we're talking about it, but these are formulas that we will start to use. And when variation of density with elevation is known, you can use this portion. So here is just a schematic for the pressure as well. In a room filled with a gas, the variation of pressure with height is negligible. So that's because to really get some change in a pressure, you would have to go, it's like the top of a mountain, right? That's where you really have to go to notice it. And we only notice it really in our breathing. So it's not like it's just non-existent. To get something like that, we would have to, break out and go into space, right? For like a drastically different one. So when we're talking about the pressure in a room, it is different. The pressure at the floor is different than the pressure at the ceiling, but it's negligible. And therefore we really just ignore it. We don't really change it. This 0.006, we're just typically don't even include it. And so then here, pressure in a liquid at rest increases linearly with distance from the free surface. So this changes in a linear relationship when we're talking about a liquid at rest. Okay, and then we've got all these different ones that you can kind of think of this as maybe like a seafloor or something like that. Or under hydrostatic conditions, the pressure is at the same points on a horizontal plane in a given fluid, regardless of geometry, provided that the points are interconnected by the same fluid. What does that mean? That is a whole lot of everything, right? Let me pause this and get my drawing board, and I will give you an example that's much easier to understand, because this is not doing it for me. All right, so the thing that I think is easier to think about is, I know it's strange, but let's say you are a cave diver, okay? And this is you, with your little cave diving stuff. Here's your little tank. Okay, so say this is the opening for the cave, and you're going to go down, and the cave goes all kinds of different ways, right? And there's your exit, okay? So here is the path. It's all underground, right? Let's actually start like up here. The way it's all underground. Okay. Okay, and it's blue. Here's all the water. And it's all one continuous water. See, I'm not picking my pen up. I'm not moving. This is all water. Crude drawing. I'm very sorry. I did not go to school for art. Okay. So when we talk about you are right here, okay? And regardless of geometry, this geometry is all over the place, right? It's not a square. It's not a swimming pool, anything like this. Right here, let's say the pressure is equal to 1 at this line, okay? So the pressure is also going to be equal to 1 here, because regardless of geometry, if we are in one continuous fluid, the pressure is going to be the same. So let's say you dive down here, and you're now right here, right in this portion. Okay, there you go. So you have dived down there to here. Okay, let's just pretend my line is very straight, very, very accurate. Okay, so my pressure here, so this is my P1, this is the first start, and that's going to be the same. My P2, my pressure at my second point, Let's just say this is 3, okay? So I know that if I need to find, what if I need to find the pressure right here? Well, then I know that my P here is going to be 3 because it's right here because it's one continuous fluid, right? And then the same for here. The pressure at all of the points on this horizontal, well, not that one because it's in the ground, but right here, the pressure at all these points in the one continuous liquid is going to be 3 because we're on a horizontal plane. Same for here. All at one continuous portion. Everything within this continuous liquid. Okay? Hopefully that helps more than that. It is very important to know because we're going to have to find that, right? So under hydrostatic condition, the pressure is the same at all points on a horizontal plane in a given fluid, regardless of geometry, provided that the points are interconnected by the same fluid, right? So here we have point A, point B, point C, point D, point E, point F, point G. They're all the same, right? Point H is not equal to point 1 because this is in mercury. It's not the same fluid, right? Because fluids have density. They have their own density. So because of that, whoops, there you go. Because of that, you can't have the same pressure if you have different fluids. So for Pascal's law, the pressure applied to a confined fluid increases the pressure throughout by the same amount. Okay, so that's just a given law. Here's the area ratio is called the ideal mechanical advantage of a hydraulic lift. We're not going to go too much into this. We're just going to, work problems with pressure. And then, of course, they have pressure measuring devices. The atmospheric pressure is measured by a device called a barometer. I'm sure you've heard of that. And thus, the atmospheric pressure is often referred to as the, some people call it barometric or barometric pressure. A frequently used pressure unit is the standard atmosphere, which is defined as the pressure produced by a column of mercury, which 760 millimeters in a height of 0 degrees Celsius. And you've got that row there. Under standard gravitational acceleration, remember we've got that gravitational constant because we're here on Earth, 9.807 meters per second squared. And so right down here, you've got a formula for atmospheric pressure here. Okay? And then remember we talked about vacuum pressure, atmospheric pressure, gauge pressure, things like that. So you'll start to see these in the schematics. Okay, and then the length of the cross-sectional area of the tube have no effect on the height of the fluid column in a barometer. Okay, provided that the tube diameter is large enough to avoid surface tension, capillary effect. So as long as it's large enough, then you won't achieve a capillary effect, then it doesn't really matter what the cross-sectional area, how wide that tube is. You're still going to get the same information. And then at high altitudes, a car engine generates less power and a person gets less oxygen because of the lower density of air, right? So we talked about that it's really negligible when you're talking about something inside of a room, that you really have to get out and achieve those high altitudes. Okay, and so then we are going to talk about different pressure measuring devices. And so one is a manometer. So this is just a very simple U-tube manometer with a high pressure applied to the right side. So the right side is where that higher pressure was applied. And then the manometer is commonly used to measure small and moderate pressure differences. A manometer contains one or more fluids, such as mercury, water, alcohol, or oil. And remember, when you're talking about, you see 1 and 2 right here. Remember, so we're talking, this is when we start looking at pressures in a continuous fluid. So you see that you have 2 fluids. You have one that's denoted with a brown. It doesn't even dictate what it is. And then you have a gas, which is also a working fluid. And so here you've got 0.1 and 0.2, that those are the same, right? And then you're able to measure that point H of a difference there. And so it's just a very basic manometer. We'll do some small calculations, but nothing, too copious here. And then right here you have P2. Here's the formula. So P2 equals the pressure, the atmospheric pressure, plus rho GH. So you'll be using that a lot. And remember, G is just that constant, 9.807 meters per second squared. Okay, and then you have pressure measuring devices just continued. You have additional information for atmospheric pressure, adding all of those together to equal P1. Okay, so of course you have the atmospheric pressure, which is just going down. Let's see if I can use my pen and write on this. So right here, yeah. So atmospheric pressure is always going to be bearing down, right? Always going to be bearing down. And then, so if you want to know what the point is at point 1 right here, you have rho GH 1, rho GH 2, rho GH 3, plus atmospheric pressure. So you need to add all of these up, right? Okay, and so then you can just pull out and add them all in and simplify it. So in a stacked up fluid layers at rest, the pressure change across each fluid layer of density, which is rho, and the height, which is h, and is rho GH, right? So you have density of each fluid, because each fluid has its own density, right? G, constant. You can pull that out, that's fine. And then you have the height, which is denoted over here that you would calculate. Okay, so here again is just some more information about, maybe we're looking at like this flow section, and you've got over here a manometer, right? We're talking about point A, point B, right? So you need to know where your pressures are. You've got rho 1, you've got a density here, you've got a different density here, of course, because you have 2 different fluids. And it just talks about how to calculate it. So if you need the pressure at point 2, so this is 2, if you want a pressure there, you would do P1, right? Because look at the arrow right here. You would do P1 plus rho 1 G, and then you've got a cross-sectional A, because plus your height. And then you're going to deduct 2 from there. So you're going to deduct all of this from all of this to get this, right? Makes sense? It kind of breaks it down. It'll make much more sense when we start working it all. But measuring the pressure drop across a flow section or a flow device by a differential manometer, and you know that from the deduction from the minusing. Okay? And so here's some other pressure measuring devices. We won't really go into too many, but you've got a Borden tube, and you've got pressure transducers, strain gauge pressure transducers, piezoelectric transducers, and they're also called solid state pressure transducers. Some of these, sometimes you'll include some of these in maybe specimens that you're testing or things like that, but we're not going to really get into too many of them. This is just letting you know that honestly there's a ton of pressure measuring devices that you can use. Just depends on, what you're measuring and what you need to use. Okay, this one you've probably seen a ton, or at least schematics of it, and you see pistons, very common. So this is a dead weight tester, and it can measure extremely high pressures up to 10,000 psi in some applications. And so it's very simple. You've just got the internal chamber with that working fluid of oil. And you do have an oil reserve because the piston goes up and down. You've got a reference pressure port, and then you've got a crank with an adjustable plunger. Okay, and so this here talks about problem-solving techniques. And I will say that when we start working problems, I will also give you some additional information on how to solve a problem. But when I solve a problem, this is how the kind of format that I tell my students to really, really look out for. And so what I do is I say, hey, what's your problem statement? Okay? What is your problem statement? This right here, what do you need? Right? So if the question is asking you, find P2, your need is to find P2. That's what you need. You need the pressure at the second state. That's what I need. Put that problem statement right up top. All right? Because you need to know where you're going before you start trying to go. And then, which for me and the students that I have taught, so it's tried and true, draw the schematic, right? So if you're not sure what's going on, but you know it's a piston because it says it's a piston, draw your piston. Draw your piston right here. And, that's not very good, but here's your system, that you're working with. And what if you need, here's P1, and then you've got a process. Something happens, maybe there's compression. Let's say there's compression. So this goes down. Okay. And right here, and this is P2, right? So say you need to know, what P2 is. That's what it wants to know. Then draw your schematic so that way you can start looking into, well, I know I have atmospheric pressure right here. I know that I have that, so I need to include that. Oh, what about the weight of this piston? What if there's a weight to this? So is there heat under here? Is there something heating it up? So just things like that. What is this force that is being applied? So things like that. That way you can start looking at saying, oh, I actually completely forgot the atmospheric pressure. I don't even have it on my schematic. So draw the schematics, get really in tune with drawing those so that you can pinpoint what you need. And then you need to write your assumptions, right? One that you don't really need to write is, hey, we're on Earth. I know that we're on Earth. You don't have to write that every time you calculate something like that. But those assumptions, maybe you assume that it's an ideal glass. Maybe when we start working, it'll make sense. But maybe one of the things is saying, well, I'm assuming that this is an ideal gas. So I'm going to use the ideal gas law, right, which is a formula. Or, I'm assuming that this is at rest, so that you can calculate it because we need assumptions and approximations to get somewhere, right? Because I said it in the last lecture, we will never get anywhere if we don't make some assumptions and some approximations. The physical law is when we're talking about different laws, we have PV equals MRT. And so that's a very common one that we use. So you can use the first law, things like that. And then you've got properties. This is when you start using the tables. You'll go to the tables. And remember, you need two independent properties to get a third. So maybe, you don't have P because you're trying to find P, but maybe you've got temperature and volume. So you can go to the tables because you can use both of these to find it. And then you start calculating. So you don't start calculating until the very end. You don't start calculating until the very end. Because if you don't have 1 through 5, you absolutely will not get an answer for 6. And with that being said, I do look at everything, right? I look at everything here. And because of that, when you get to your answer, I want everyone to write this down. When you get to your answer and you get a final answer, because you're going to get a lot of other answers that's not your final answer, I want you to put a huge box around it. Square, rectangle, whatever size you need it for. This is a rectangle. Box your answer in, because that is the final answer. And there's a lot of times, some of these calculations that you're going to be doing is pages long. So please note your final answer, because there is a lot of times I will get students work and I can't even find the final answer. Box it in so that you don't get counted off. because if I see your final answer, then I can backtrack. But a lot of this is sometimes going to look a little bit gibberish. You're going to be in a time crunch. Box it in. That will make me able to grade and give partial credit to things like that. And then you've got step 7 is reasoning, verification, and discussion. This, meh. Unless I'm going to ask you to discuss your answer, don't spend your time discussing your answer. Unless I'm going to ask you to provide like a proof for it or reasoning, do not spend your time on tests doing things like that. Now, for you to make sure that your answer is right, to double check yourself, to self-check yourself, absolutely do that. This is a great technique for making sure that you have the right answer. Don't spend time making this perfect to turn into me, okay? Because this is what I'm grading, and all of this above it. I'm going to grade this. I'm not grading this. Unless I ask you to discuss a problem, I'm not going to grade you on a discussion, okay? Let's see. So here we've got additional, this kind of comes in here, given. This is a really good example. You can kind of switch both of these. Doesn't matter. You can use given or to be found. If you know that, P1 was given to you, T1 was given to you, temperature at state 1. If those things were given to you, then you can just write down those givens and then what you need to be found. But this stuff needs to go up top. You need to know where you are and where you need to go before you can start going from there to find your missing information, what you need. Okay? And then you've got, assumptions. Take P equals 1 atmospheric pressure, right? And then you've got other assumptions. This schematic right here is actually really accurate, very accurate. And students find this. I hope you find it a lot sooner than some students. Some students will just go right out the gate and calculate. I'm just going to calculate. I'm just going to calculate all the way up here, and they never make it. So definitely do the work. Definitely do all of this tedious stuff. And also, I cannot give you partial credit on just some random calculations, but I can give you partial credit if you know what you have. I can give you partial credit if you know where you need to go. I can give you partial credit if you know what you need to find. Even if you can't find it, I can give you partial credit if you identify it, right? If you assume right assumptions, I can give you partial credit, but I can't give you partial credit on gibberish calculations if you're not sure where to go. So this right here will guarantee you some points if you know what you're doing. This right here, you may still get there. It's not advisable. Not advisable for sure. Okay, and here I'm not going to go into, of course it's important to be neat. Of course. Okay, and so you know what? One thing that is really important is there's a lot of tools. There's a lot of tools for thermodynamics and calculating thereof, especially in the industry. They use calculations. They use calculating software to do some of the hand calculatings that you will be doing. However, you have to be able to get the data and to know what those things are solving for you to be able to put it into the data. So that's why you learn how to do it first, right? If you don't know what the software is doing, you'll never know what to put into the software because it's not like you can just check a bunch of boxes, put it all into like a calculator and hope it works out, right? If you didn't know how to add and subtract, you could get nowhere with a calculator because you wouldn't know what it was doing. So same technique here. We have equation software. You can use Excel. I'm actually way okay with that. Some of the stuff that you're going to need, it may be beneficial here. It's actually not something that I use it for. But it is something that you can, unless you are just a wizard and you use Excel all the time, like all the time. I don't recommend you delving into that. It could be more cumbersome than beneficial. And, oh, you know what? We've got significant figures. So this has rounding to 3 sig figs. When I'm talking about what to give an answer for, now we're going to be using, things that actually it should denote what the problem should say. Well, round to 4 decimal places, round to 2 decimal places, things like that. However, I will tell you as a personal recommendation and as something that I follow throughout, you're going to have calculations going down the page, and you're going to be rounding at tons of steps in here. And all of those roundings are going to carry on and can definitely compound to a wrong answer here. For me, if the answer says 4 decimal places, then round out to 6 every step of the way until your answer. So your answer should be in 6 decimal places and you should just round out. If it's 2 decimal places, start out at 4 up here. Start out at 4 up here and round down. So start calculating 2 decimal places higher than what your problem is asking for. Okay? And so in here we've talked about, properties about how, the first law denotes that energy is a property, right? That's really important. Thermodynamics, the change heat, right? And energy, which is a property, it established it. And then the importance of dimensions, huge. Systems and control volume, talked about that, and how to define a system, whether it be with a boundary that's real or imaginary. Density, it's different. It's denoted by rho, but remember it's different for each working group, working fluid, and you've got specific gravity. States, think of that. I'll draw a little camera. It's like taking a little snapshot of your system in equilibrium. Everything's trying to reach that. Processes and cycles, it's like a clock, right? When you go back around, that's a cycle, okay? And then a process is just, A to B, and you've got a path right here, right? Temperature in the 0th law, all you need to know about this is how we have temperature. That's it. Temperature, 0th law. That's all we're going to do with that. Pressure, you're going to have lots of pressure and pressure measuring devices, tons of them. You've got the barometer, right? You've got just tons of them, manometer, tons. And then problem solving techniques, tons of different things. I will even require a format on any work that you turn into me directly. But when you do, just remember, unless you're putting your answer into an actual program, if you are turning in information or scratch work or something to me or a program, you want to box your answer in. That's what I need. All right, I think that's it. Yep, okay. All right, I'll see you next lecture.